Hello everybody. This is an example problem with writing the equation for a position versus time for a simple harmonic oscillator. So a little more of a complex problem here, where we've got some more calculations, a few more steps involved in solving this one. So the first part on this problem is that we have a mass that's hung from a spring, and then we're told how far that makes the spring stretch. So if we imagine this, we've got a spring with nothing hanging from it, and then when we hang our mass, we get down like this. And it tells us that this distance is 0.25 meters, and the mass is given as 5 kilograms. So that information we can use to figure out what the force constant for this spring is. The idea there is that K, the spring constant, is equal to the force divided by the distance stretched, X. And in this case, the force applied is going to be, well, it's the force of gravity from that 5.0 kilogram mass. So that'd be 5 kilograms times 9.8 meters per second squared, divided by the distance stretched is 0.25, that's meters. So we get a spring constant here of 196 newtons per meter, or kilograms per second squared. Both units work for a spring constant here. Now from there, we can figure out how much time it takes to oscillate once. And that's going to be where we're able to start plugging in and finding an equation for this. So the period for mass on a spring system is given by 2 pi square root m over k. And now we know what our k value is, so we can plug in there. So t is equal to 2 pi times square root 5 kilograms divided by 196 kilograms per second squared, and those units work out nicely now. Our kilograms will cancel. Leaves us with 1 over seconds squared under the square root there, or just seconds squared. So 2 pi times square root of 5 over 196, we get a period of 1.00 seconds. Alright, now also in this problem, it tells us that we have an amplitude, or it tells us that the mass is raised by 5 centimeters from equilibrium and then released. So we have an amplitude of 5 centimeters, or 0.05 meters, if that's more convenient. So sometimes on these I think it's useful to just kind of sketch out the graph. So here we have it raised up to some height, that's our initial position, and then it's going to oscillate back and forth here. And we're told, or we figured out that it's going to take 1 second for a complete cycle, and that we have a maximum displacement of 5 centimeters. So now we need to write the equation for that graph. These equations are going to take the form of x equals a sine or a cosine. The equation sheet for AP Physics uses a cosine here, but they're the same shape, just shifted by 90 degrees, so either one would be fine, times 2 pi f t. F we don't have right now, but we can find f as 1 over the period, and the period is 1 second, so 1 divided by 1 is just going to give us 1 hertz. And then it's a pretty simple matter here to plug in for each of the quantities in the equation. So x, I should write x as a function of t, is equal to a, the amplitude, that's 5 centimeters, or you could change that to meters, either way is fine, times the cosine of 2 pi times 1. and that's hertz times t. Hertz is the same as 1 over seconds, so you might also see this written out as x as a function of t is equal to 5 centimeters cosine of 2 pi over seconds, 1 over seconds, times t. And you see if we have seconds for our time here, the seconds are just going to cancel out, and we'll just have some angle in radians inside the parentheses there, which makes sense for the cosine function. The other thing we can do is shift this graph over if we need to. Cosine starts with a value of 1, and we see here that, that this graph starts at its maximum value as well, so we actually don't need to shift this one. If, for example, though, we started, maybe something more like this, where we don't start at our maximum value, we can write out our equation as x of t is equal to 5 centimeters times the cosine of 2 pi times 1 over seconds for our units times t, and then we can just add a term inside the parentheses that shifts this over. So on this one, cosine starts at a maximum value, so cosine would start right here or right here. This one we're starting at a value of 0, so I'm shifted over by, that's a quarter of a cycle. A quarter of a cycle in terms of radians would be pi over 2. Now if I add pi over 2, what that would do is shift it over so it starts over at this point instead of starting over here. So what I actually need to do is add 3 pi over 2 so that our starting point is right here. We start at equilibrium and move up from there, as we did over here, start at equilibrium and move up. So we could do plus 3 pi over 2 minus pi over 2 would accomplish the same thing here. So if you care, we have the option to shift our graph left and right just by adding a term inside the parentheses here. Generally, all we're going to care about here is the shape, but it's an option if we need it. The other way that we could write that same expression, or the equation for the same graph, would be not to use cosine, but to use sine instead. So we could do 5 centimeters times the sine of 2 pi, 1 over seconds is the unit on that, times t. Because sine starts at a 0 value and goes up from there, just as this graph starts at a 0 value and goes up. So sine might be a better fit there anyway. Either way, we get the same shape, the same results. Thank you very much. If you've learned anything from this video, go ahead and hit like, or if you think you're going to learn something more from future videos, please subscribe to the channel.